Have you ever come across a mini fridge that hums silently with no moving parts? Or a compact laser system that stays perfectly cool without a fan? Chances are, you're looking at the power of a Peltier module, a compact, solid-state device that can move heat using electricity. In this video, we're diving deep into the world of thermoelectric cooling, how it works, where it's used, and why it might shape the future of energy-efficient thermal management. At the heart of Peltier modules is a principle called the Peltier Effect, discovered in 1834 by French physicist Jean-Charles Athanase Peltier. Here's the basic idea. When you pass an electric current through two dissimilar conductors or semiconductors joined together, heat is either absorbed or released at the junction, depending on the direction of current. This is different from Joule heating, which just creates heat. The Peltier effect can actually move heat much like a pump moves water. So when current flows through a specially designed thermoelectric material, heat is transferred from one side to the other. One side cools down, and the other heats up. So, what does a Peltier module actually look like inside? It's made up of dozens, sometimes hundreds, of tiny thermocouples, connected electrically in series, but thermally in parallel. Each thermocouple consists of two different semiconductor blocks, one N-type and one P-type, typically made of bismuth telluride, a material with excellent thermoelectric properties. These pairs are sandwiched between two ceramic plates. The ceramic provides electrical insulation but also helps conduct heat. When DC current flows through the module, electrons in the N-type material carry heat from the cold side to the hot side. Holes in the P-type material do the same. The result? The top surface gets cold while the bottom surface gets hot. And this happens almost instantly after power is applied. So how do we measure how well a Peltier module performs? There are four key specs you'll see. First, delta T max, the maximum temperature difference it can maintain between hot and cold sides, often around 60 to 70 degrees Celsius. Second, Q max, the maximum amount of heat the module can pump, measured in watts. Third, input voltage and current. Usually modules run at 12 volts or less but draw high current. And fourth, COP, or coefficient of performance, a measure of efficiency. Unfortunately, Peltier modules are generally less efficient than traditional refrigeration systems. And here's the catch. As the heat load increases, or if you don't cool the hot side effectively, the cold side starts to heat up too. So, effective heat dissipation is crucial for performance. Despite their limitations, Peltier modules are used in a wide range of applications, thanks to their compactness, quiet operation, and precise temperature control. Let's explore a few. In consumer electronics, they're great for cooling CPUs, GPUs, or overclocked components in small spaces. In medical devices, you'll find them in portable vaccine coolers, temperature control for diagnostic tools, and even lab-on-a-chip systems. Optoelectronics benefit too, with Peltier modules stabilizing laser diodes, CCDs, and infrared detector modules. In aerospace and military settings, they help cool sensors in extreme environments. And in wearables, experimental climate control clothing uses flexible thermoelectric materials. Because they can be reversed simply by switching the current direction, Peltier modules can both heat and cool, which is a unique advantage in many control systems. Let's quickly weigh the pros and cons of using a Peltier module. The advantages? No moving parts, making them silent and very reliable. They're compact and lightweight and can operate in any orientation. You get precise temperature control, and they work in vacuum environments, which is ideal for space, but there are limitations. Peltier modules have low energy efficiency compared to vapor compression cooling. They also draw a lot of power, and you need to remove significant heat from the hot side. Plus, their cooling capacity is limited for large-scale applications. So while Peltier modules are great for small, specific cooling tasks, they're not a replacement for your air conditioner, at least not yet. The good news? The world of thermoelectrics is evolving fast. Researchers are working on new materials with a higher figure of merit, or ZT. That's a measure of thermoelectric efficiency. Nanostructured materials like scutterudites and quantum dot superlattices could significantly improve performance. At the same time, Flexible and printable Peltier materials are in development for wearable cooling, solar waste heat recovery, and battery thermal regulation. As energy efficiency becomes more critical, Peltier modules may play a key role in low-power, silent, localized cooling systems. So there you have it, a silent, solid-state technology that can move heat with nothing but electricity. Whether it's cooling a tiny camera sensor or helping preserve vaccines in remote areas, Peltier modules show how clever engineering and physics can make powerful, compact tools. Thanks for watching. If you found this breakdown useful, be sure to like, subscribe, and check out our next video on Seebeck generators, the reverse process that turns heat back into electricity.